This lecture presents techniques for solving ordinary differential equations, ODEs, in Mathematica. There are two basic functions for that purpose, DSolve and NDSolve. They differ in that DSolve solves ODEs analytically and NDSolve solves them numerically. So here's an example of the use of DSolve to solve an equation which can be solved analytically, namely a damped harmonic oscillator. So here's the use of DSolve. The first argument to DSolve is a list of the equations. First the differential equation itself, then the initial conditions. So in this case you have an equation for the acceleration of the oscillator position, and that's the part which makes it oscillate, and that's the part which damps it. So I've got a weak damping on here of 0.1, and then here's the starting point. The oscillator position starts at 1, and it starts at rest with a 0 time derivative. And then the next argument is the function you're solving for, and finally the dependent variable. So if I execute this line, I get the solution in the form of a list of solutions. There's usually only one in the list. Every once in a while an equation of some kind will have more than one solution. And each solution is itself a list of what are called substitution rules. Substitution rule is x of t goes to, and then the solution itself. To use this solution, which I've saved in the variable called solution, we typically use it to define a function. And here's an example of how that's done. So first we want the first and only solution, so we take solution sub 1, the first element in the list of solutions. And then we take x of t and substitute it by that solution. So slash dot can be read as substituted by. So this is x of t substituted by this rule. And then we immediately assign that to be the definition of a new function f. And note the special notation for defining a new function. This is read as f of a single argument called t. So this underscore is telling you that this is a definition for a kind of generic t. Anyway, this is the syntax for defining a new function. Having done this, so I'll execute it now, the function acts like any function that already exists. You can evaluate it, and you can plot it, and so we can see the decaying oscillation of the oscillator. DSolve can also solve systems of ODEs, and here's an example that describes a set of coupled chemical reactions. So consider a batch reactor with two species A and B at concentration Ca and Cb. The initial conditions are that Ca starts out at some finite concentration and Cb starts at 0, and they have equations which are of this form here. There's reaction rate constants that take Ca into Cb and so on. Anyway, these are two coupled equations. And so you want to solve those and plot their solutions as a function of time for particular values of the rate constants Ka and Kb and a particular value of the initial concentration. So here I'm going to use DSolve to solve those two equations, and I write out the equations and the initial conditions in a list right here. This is the differential equation describing the time evolution of Ca. This is the differential equation for Cb. This is the initial condition for Ca and the initial condition for Cb. It's a list in curly brackets, each element separated by a comma. Each equation has double equals. That's what's used always in writing equations in Mathematica. When you're solving for more than one thing, you have to give a list of the functions you're solving for as the second argument, and then the dependent variable as the third argument. I've left Ka and Kb as just variables that I haven't defined yet, and that is possible because DSolve can solve these equations analytically. Likewise, CA0 has been left just as a variable at this point. So when I solve that, I get a list of solutions of which there's only one, and the solution is itself a list of substitution rules, and now there's two substitution rules because there's two things that I solve for. If I want to use that solution, which I've saved in a variable sol, then I use it in exactly the same way as before to define two functions, CA function of t and CB function. That's what the little f is for. It's good generally not to overuse names, so I'm trying to avoid saying CA of t equals CA of t substituted by the solution. So I just give the thing a slightly different name. And so when I do that, I've defined two new functions, and as yet I haven't said what Ka and Kb are, or Ca0. So if I want to use these functions to plot them, then I can set those parameters now, and here I've done that in just 3 lines, which I've separated by semicolons. Mostly I don't encourage beginning Mathematica students to put more than one line in a cell, but in this case all I'm really doing is just defining 3 coefficients. So I can separate those lines with semicolons and do this definition. And now you can see that Ka, Kb, and Ca0 have turned black, which means Mathematica knows a definition for them. And so I can plot these two functions. And as usual, I have used a couple of options to plot to make a nice looking plot, which looks like this. So I've put a frame on it, I've put frame labels on, and have made some choice about the label style. So the second function in Mathematica for solving ODEs is NDSolve, the N being the general Mathematica code for numerical. So this is numerical solution of differential equations, not analytical solutions. And indeed, most differential equations cannot be solved analytically in terms of functions that we have names for. For instance, here's the harmonic oscillator equation again, but this time I've made the frequency in the oscillator depend on the amplitude. The frequency gets larger when the amplitude is big, so the thing oscillates faster. And that makes the equation nonlinear in such a way that it can't be solved analytically. Nonetheless, I can, so I'll just show you that it can't be, because here I'm trying to do it with DSolve, and it will think about it for a while and eventually conclude that it can't solve it, and it will echo back what I've asked it to do. So instead, I'm going to use NDSolve to solve it, and the syntax is almost exactly like DSolve. You put a list of the equations here, which are the differential equation and the initial conditions, the position and velocity of the oscillator to begin with, the function I'm solving for, and instead of just solving, instead of the third argument being just the variable, the dependent variable, you specify the range of the dependent variable, much as if you were doing a plot. Because what NDSolve is doing ultimately is calculating a list of points between two values using a numerical procedure. So what comes back is again a list of solutions of which there's only one, and that solution is a list of substitution rules, and the substitution rule looks rather different. It says x of t goes to an interpolating function. An interpolating function is Mathematica's way of representing a function in terms of a list of points that it calculated. We use that solution, which I've again saved in sol, in exactly the same way as before to define a function. And that function, although it's an interpolating function, for our purposes behaves just like a normal function. We can evaluate it at some particular point, and we can plot it. And in the plot you can see what the effect of the nonlinearity was. The oscillation is faster over here where the amplitude is big than it is later when the amplitude is decayed to smaller values.